Welcome to lecture number 12, Fundamentals of Transport Processes, where we were looking at unidirectional transport using the method of separation of variables. This is an important solution procedure, so we will go through it in some detail to illustrate some of the intricacies involved in actually implementing it properly, because once you implement it properly, then it is a very powerful tool to be used for solving not just transient problems, but also problems involving variations in different coordinate directions. Okay. So, the problem that we were considering was as follows. This was unsteady diffusion in a finite channel. I have two plates 0 and h. Okay. The temperature at the bottom is 1, the temperature at the top is 0 in scaled variables. In the final steady state, one would expect that the temperature in the limit t going to infinity reaches a linear temperature profile, where the temperature varies linearly with position. However, the transient temperature profile is not linear. It evolves from initially 0 temperature throughout the channel to a final linear temperature profile, because I had applied the initial condition that both the bottom and the top plate temperatures were 0 initially at t equal to 0. The entire fluid was at t star is equal to 0 at time t is equal to 0, and at t equal to 0 I instantaneously switched the temperature at the bottom from 0 to 1, and then I look at how the temperature field evolves as a function of time. So, that was the problem to solve for that unsteady evolution of temperature within this channel. Okay. The differential equation that we consider is the usual one for the unsteady case with no sources and no sinks. Okay. It is just partial of temperature with respect to time is equal to alpha times d square t by dz square. Okay. And t star is equal to 0 at z is equal to 0, t star is equal to 1 at z is equal to 0, 0 at z is equal to h. We had defined the scaled z coordinate as z star is equal to z by capital H, okay, and we put into that equation and managed to get out a scaled time t star is equal to t alpha by h square. This is a dimensional necessity, because the only parameters in the problem are alpha, the diffusivity, the thermal diffusivity, and h, which is the distance between the two plates. And therefore, I can get only one time scale out of this problem, which is h square by alpha. Okay. So, I can define only one dimensionless time as t alpha by h square. So, that was the rationale for choosing this dimensionless time. Physically, this can be interpreted as follows: alpha by h square. Okay. So, if the time is h square by alpha, that is the time it would take for thermal diffusion of energy over a distance proportional to h. Okay. So, this h square by alpha is a time scale over which you would expect diffusion of heat over a distance comparable to h, and therefore, equilibration of the temperature field over a distance h. So, when t is large compared to alpha by h square, that diffusion has already taken place over the entire extent, and the system has reached a final steady state. When t is small compared to alpha by h square, the diffusion does not progress very far. Okay. So, because of that, it is confined to a thin boundary layer near the surface of a penetration layer, okay, of depth is equal to square root of alpha t. Okay. So, t star, okay, gives me some indication of the time over which diffusion would take place. If t star is large compared to 1, or t is large compared to h square by alpha, I would be attaining the steady state temperature, whereas if t star is small compared to 1 or t is small compared to h square by alpha, the temperature should be in the very initial stages of development, where the penetration depth of the temperature into the medium is small. Okay. So, that is the physical interpretation of this time scale t star. When expressed in terms of the scaled time and the scaled coordinate, the final equation that I get has no dimensional parameters in it. Okay, so, it is a completely dimensionless equation when expressed in this form. Okay. As I said, in the limit as time going to infinity, I should reach the final steady temperature. Okay. That final steady temperature was equal to 1 minus z star. Okay. And that satisfies the equation d square t by dz star square is equal to 0, okay, with temperature is equal to 1 at the bottom and 0 on top. So, in the final in the limit as t going to infinity, you should reach this final steady state temperature. Okay. So, before progressing, we made a decomposition in the temperature. Okay. We wrote it as two parts. Okay. One is a steady part and the other is the transient part. Okay. The idea is that if the system reaches the final steady state, the transient part has to go to 0 and T should just be equal to Ts. Okay. So, therefore, the transient part of the temperature is the correction to the temperature profile for T being of order 1 or small. In the limit of T being large, this will go to 0. Okay. So, having separated the temperature into a steady and the transient part, we have to separate the equations also into individual equations for the steady and the transient part. The steady part d square Ts by dz square is equal to 0 is the equation for the steady temperature profile. Okay. With boundary condition Ts is equal to 1 at z is equal to 0 and Ts is equal to 0 at z is equal to 1. Hot at the bottom, cold on top. Okay. For the total temperature field, that is T star is equal to Ts plus the transient part, I can write the same differential equation once again. Partial of Ts plus Tt by partial time is equal to the second derivative with respect to z of the transient plus the steady part. The steady part is independent of time, so its time derivative is 0. The steady part also satisfies d square Ts by dz square is equal to 0. So, my differential equation for the transient part reduces to just a simple form, the exact same form that I had for the original temperature profile. dt transient by dt star is equal to 0 and is equal to d square t transient by dz star square. However, there is a difference in the boundary conditions. Okay. For the steady part, I have Ts is equal to 1 at z is equal to 0. Ts is equal to 0 at z is equal to 1. For the steady part, for the total temperature profile, I have Ts plus Tt is equal to 1 at z is equal to 0. Ts plus Tt is equal to 0 at z is equal to 1. Subtract the 2 and I will get T transient is equal to 0 at both z is equal to 0 and at z is equal to 1. So, as I said, these are homogeneous boundary conditions. Okay, in the z coordinate. The transient part of the temperature is 0 both at z is equal to 0 as well as at z is equal to 1. So, it satisfies homogeneous boundary conditions in the z coordinate. Okay. However, even though the boundary conditions are homogeneous in the z coordinate, they are not homogeneous in time. Okay. At time t is equal to 0, the initial condition for the temperature field was that T star is equal to 0 at all z greater than 0. Okay. T star was equal to 0 for all z greater than 0. That means the transient plus the steady part has to be equal to 0 at all z greater than 0. Okay. That means for the transient part alone, the boundary condition is T transient is equal to minus T steady state at z is equal to 0, okay, or T transient is equal to minus 1 minus z star. Okay. And it explained the physical significance of this in the previous class. Okay. These homogeneous boundary conditions in the two spatial coordinates means that there is no temperature forcing for the transient part alone at the two boundaries. The steady part does have T star is equal to 1 at z equal to 0 and T star is equal to 0 at z is equal to 1. But for the transient part, the boundary conditions are both T star is equal to 0 at both z is equal to 0 and z is equal to 1. Whenever boundary conditions are of the form either the temperature or its derivative is equal to 0, these are referred to as homogeneous boundary conditions, because there is no forcing over there. Okay, there is no finite temperature that is imposed at those boundaries. However, the initial condition is not homogeneous. Okay, you have a non-homogeneous initial condition, which is actually the reason why t transient is not equal to 0. Okay. In the limit as t going to infinity, it will of course decrease to 0 in the long time limit, but at intermediate times it is not equal to 0, because the transient temperature field has been forced at the initial time, okay, at t star is equal to 0. Okay. So, the solution of these equations, okay, we had briefly started it in the previous lecture, a method called separation of variables. Okay. So, we write this temperature, which is a function of z and t, okay, as the product of two terms. One is the function only of z and the other is only a function of t. Okay. So, the functional form of the temperature function of both z and t is separated into two parts, one of which is only a function of z, the other is only a function of t. Okay. And this is put into the equation. Okay. So, I get d by dt of z theta is equal to d square by dz star square of z times theta. Okay. Note that z is only a function of z star and theta is only a function of t star. Okay. So, this I can write it as z times d theta by dt is equal to theta times d square z by dz star square. Note that I have used the total derivatives d here. The reason is because theta is only a function of t, therefore, the partial derivative is also equal to the total derivative, because it is only a function of one variable. Similarly, z is a function only of z star, okay, therefore, it is a total derivative. I divide throughout by z times theta, okay, to get 1 over theta d theta by dt is equal to 1 over z d square z by dz star square. Okay. Now, in this equation, the left hand side is only a function of time and the right hand side is only a function of z. Okay. That means that both of these are equal to constants. The reason is as follows. Let us assume that it is not equal to a constant. Okay. Let us assume that the left hand side is only a function of t and the right hand side is a function of z and both are equal. Okay. In that case, I can keep z a constant and change t. Okay. If I do that, the left hand side changes, the right hand side does not, because I kept z a constant and changed t. So, if the left hand side changes and the right hand side does not, then the equality is no longer valid. Okay. Conversely, I can keep t a constant and change z. In that case, the right hand side changes and the left hand side does not. Okay. And therefore, I will end up with a situation where the equality is no longer satisfied. The only way that the equality can be satisfied for all values of z and t is if both of these are equal to constants. Okay. So, therefore, I require, just from the condition that the left hand side is only a function of t, the right hand side is only a function of z, From that I can infer from an equation of this kind both of these left and the right hand side has to be a constant. So, what is that constant? Okay. Now, let us look at how to solve for this constant. Okay. So, I have an equation 1 over z d squared z by dz star square is equal to some constant alpha. Okay. Is that constant positive or negative? Okay. Let us try to solve this and see. Okay. So, therefore, the equation d square z by dz star square is equal to alpha times z. Okay. For the moment, we will assume that this constant is positive. Okay. The solution of this will be of the form z is equal to a e power root alpha z star plus b e power minus root alpha z star. Okay. Now, what are the boundary conditions for z? I have got two constants. I have solved a second order differential equation and I have got two constants. Okay. And those two constants now have to be determined from the boundary conditions for z. Okay. What are the boundary conditions for z? I require that the temperature has homogeneous boundary conditions both at z is equal to 0 and at z is equal to 1, the temperature is 0. It is 0 at all times. Okay, it is 0 at all times. Therefore, I require that z has to be equal to 0 both at z star is equal to 0 and z star is equal to 1. So, therefore, in this case I require that boundary conditions z is equal to 0 at z star is equal to 0 and z is equal to 0 at z star is equal to 1. Okay. Insert those boundary conditions here and I will get a plus b is equal to 0 and a times e power root alpha plus b e power minus root alpha is equal to 0. Okay. I just put z star is equal to 0 in the first equation, z star is equal to 1 in the second equation. From these equations you can easily see that the only solution that I will get is that a is equal to 0 and b is equal to 0, which means that capital Z is equal to 0. Therefore, in this case I do not get any non-trivial solutions for Z. Okay. The solutions end up just being the trivial solution that Z is equal to 0 everywhere. Okay. And therefore, T transient will be equal to 0. Okay. Now, that was because I happened to choose a value of alpha which was positive. Okay. What happens if I choose a value of alpha that is negative? Okay. So, let us look at that. Okay. This was one particular choice of alpha. Okay. Let us look at some other negative choice of alpha. Okay. So, I will take the equation of the form is equal to minus some constant square. Okay. So, that this beta is negative. So, that the constant that I have here is a negative value. Okay. Beta square is always positive and therefore, the right hand side is negative. The equation reduces to d square z by dz star square is equal to minus beta square z. Okay. The solution for this is z is equal to a cos beta z star plus b. Let me write it the other way. A sine okay, a sine function and a cos function. So, the solution is a combination of a sine and a cos function. The boundary conditions, z is equal to 0 at z star is equal to 0 and z is equal to 0 at z star is equal to 1. Okay. Z is equal to 0 at z star is equal to 0, sine is 0 anyway. So, therefore, I require that b is equal to 0 from the first condition, because at z star is equal to 0, sine of 0 is 0, cos of 0 is 1. So, therefore, b has to be equal to 0. At z star is equal to 1, since b is already equal to 0, I require that a sine of beta z star has got to be equal to 0. Okay. One option is, of course, that a is equal to 0, in which case I do not get any non-trivial solutions. Once again, okay, I get just the trivial solution. But wait, there is another possibility, and that is that sine of beta z star is equal to 0. Okay. If sine of beta z star is equal to 0, then the boundary condition is satisfied. Okay. But for that, I require to take beta to be specific values. Okay. If I take beta is equal to n times pi, okay, where n is an integer. Okay. I will call this as beta n. Okay. So, where n is any integer value. Okay. So, n is equal to 0, sine of 0 is 0, n equals pi, sine pi is equal to 0, okay, z star is 1, 2 pi, 3 pi, etc. Any value of the integer will satisfy this equation. Okay. So, I do get non-trivial values for the solution of this equation, but I have to choose the value of beta to be specific values. Okay. So, therefore, this initial this first guess that we had of a positive value, okay, did not give any non-trivial solutions. Okay. So, I choose a positive value, I did not get any non-trivial solutions. However, when I chose a negative value, I managed to get a non-trivial solution, okay, but only for the case where this coefficient beta has a specific value. So, therefore, the solution for the case where beta has a specific value is z is equal to sine a sine beta n z star, is equal to a sine of n pi z star. Okay. What about the other part of the equation, which was the variation in time? So, this was equal to minus beta square. So, this is also equal to minus beta square. Okay. So, therefore, I can solve for the second part of the equation. Okay. 1 by theta d theta by dt is equal to minus beta square, okay, which is minus n pi the whole square. Okay. Or d theta by dt star is equal to minus n pi the whole square theta, okay, or theta is equal to e power minus n pi the whole square times t star. Okay. Now, we had chosen the value of beta, we had chosen the constant to be negative, okay, because we got a non-trivial solution for this constant beta here, okay, in this particular equation. Okay. We had chosen it to be negative, so that we got a non-trivial value of the value of the beta for the separation of variables problem for this equation. Okay. If we chose it to be positive, we were getting equations, the solutions to just be 0. Okay. However, that is consistent with the solution that I am getting for t as well, okay, because I am getting something that is exponentially decreasing in time, okay, and the transient part will go to 0 only if it decreases exponentially in time. If I had chosen the constant here to be positive, I would have got solutions that increase exponentially in time, and clearly that is not going to reach a steady state. Okay. So, I require solutions that decrease exponentially in time, and therefore, I require this constant to be negative. Okay. So, therefore, both of these parts of the solution of the separation of variables are consistent with each other. So, let us put all of that together, and finally, we get T t is equal to a sin n pi z e power minus n square pi square t. So, this is one solution, it satisfies it if n is any integer. Okay. So, this satisfies the differential equation and the boundary conditions if n is equal to 0, 1, 2, 3, etc. So, no matter what the value of n, this form of the solution satisfies the boundary condition, okay, as well as the differential equation. We still have not imposed the initial condition. We will come back to how to impose that a little later. Okay. But this is one particular solution of the differential equation which satisfies both boundary conditions. This is true for n is equal to 0, n is equal to 1, etc. Okay. So, the most general solution is the sum of all of these solutions. Okay. So, the most general solution that I can get is sum n is equal to 0 to infinity of a n times this. Okay. So, since it satisfies it for n is equal to 1, satisfies it for n is equal to 2, n is equal to 3, etc., the most general solution is one which is the summation of all of these solutions. Okay. Now, we have to determine what is the coefficients a n. Okay. We have to find out what these coefficients are in order to find out what the final solution is. These coefficients can be determined using something called orthogonality conditions. Okay. And these conditions are defined on the domain between 0 and 1. Z star is equal to 0 to Z star is equal to 1 was the domain of interest, okay, and these orthogonality conditions are defined on that domain. Okay. These are easy to do by simple integration. If I take integral 0 to 1 dz star sine of n pi z star sine of m pi z star. Okay. So, if I just take two functions sine of n pi z star and sine of m pi z star and integrate from 0 to 1, okay, this is equal to 1 by 2 if m is equal to n, and it equal to 0 if m is not equal to n. So, in a sense, these functions defined on this domain 0 to 1 are all orthogonal to each other. Okay. If you take one function, multiply it by itself and then integrate it from 0 to 1, you get a half. If you take one function, multiply it by some other function, integrate from 0 to 1, you will get 0. Okay. So, every function when integrated with any of the other functions, all the way from n is equal to 0 to infinity, it ends up being 0. How does this help us? Okay. The initial condition we wanted was T star transient is equal to minus of 1 minus z star at t is equal to 0. Okay. So, this was equal to minus the steady state temperature, because T transient plus T steady was equal to 0 at time t is equal to 0. Therefore, T transient was equal to minus of 1 minus z star at t is equal to 0. Now, we have the solution. We have the solution for the temperature field. Okay. Therefore, at T star is equal to 0, T star transient is going to be equal to sum n is equal to 0 to infinity of a n sine of n pi z star. Okay. And this from the initial condition has got to be equal to minus of 1 minus z star. So, I have to determine all of these coefficients a n all the way from n is equal to 0 to infinity from this particular equation. Okay. So, in general you are solving for an infinite set of coefficients, okay, in order to find out this equation contains an infinite set of coefficients. But this is where the orthogonality relations can be crucial in determining each of these coefficients, and that is done as follows. Okay. So, this equation that I have I take both the left and the right hand sides multiplied by sine of m pi z okay, so multiplied by sine of m pi z and then I integrate this from 0 to 1. So, okay, I multiply by sine of m pi z on both sides of the equation, and I integrate from 0 to 1. Okay. On the left hand side, what do I get? Okay. Summation n is equal to 0 to infinity times a n times half times something which is 1 if n is equal to m, and it is 0 if n is not equal to m. Okay. This thing I will call it as the delta function. Okay. This delta m n is 1 if n is equal to m, and it is 0 if n is not equal to m. Okay. So, I just get half a n times delta m n. Sine of Now, on the left hand side I have the summation of delta m n times a n from n is equal to 0 to infinity. So, I have a n going from 1, 2, 3, 4, 5, 6 all the way to infinity, but delta m n is non-zero only when n is equal to m. Okay. So, if for example, m is equal to 23, delta m n is not non-zero only when n is equal to 23. Therefore, on the left hand side I will get only a 23. If m is equal to 2, then the only term on the left hand side I will get is a 2 divided by 2. Okay. So, this summation Since it is non-zero only when n is equal to m, this can effectively be written as half a m. Can effectively be written as a m times this. Okay. So, this now gives us each and every one of the constants in that expansion. So, a m is equal to minus 2 integral d z star 1 minus z star sine of, okay. And you can evaluate this constant, okay, and this turns out to be equal to minus 2 by m pi. Okay. For odd m is equal to 0 for even m. Okay. So, putting all these together, okay, with this coefficient for m, okay, I get finally the transient temperature field T star is equal to minus summation n is equal to 1, 3, 5 etcetera to infinity of 2 by n pi sine of n pi z star e power minus n square pi square times T star. So, that is the final solution for the temperature field. Okay. This is only the transient part. You can see that it is equal to 0 at z is equal to 0, it is equal to 0 at z is equal to 1. It is equal to 0 in the limit as t goes to infinity. Okay. Everything that was required of the transient part of the temperature field. The total temperature is equal to this plus the steady state, that is 1 minus z plus minus 2 by n pi sine of n pi z. Okay. So, that is the final solution for the temperature field. Okay. You can see that the higher order terms in the expansion are decaying exponentially as e power minus n square. So, at any finite time, these higher and higher terms will become smaller and smaller, because as n increases, this exponential is going as e power minus n square. So, because of that, the higher order terms will decay even faster. So, if I want a good numerical approximation, I can cut off this series at some particular finite value of n, and I will get a good numerical approximation for this temperature field. So, we managed to get a mathematical solution for this temperature field. How about a physical feel for what it all means? Okay. What do these orthogonality relations mean? Okay. So, let us assume that I define two functions S n is equal to sine of n pi z and S m is equal to sine of m pi z. I can define what is called an inner product, okay, of these two functions. Okay. I will use angular brackets for here, S n comma S m, okay, is equal to integral 0 to 1 d z S n of z S m of z. Okay. And I did the calculation to show you that this is equal to delta m n by 2. So, these two functions are orthogonal to each other, okay, in a similar sense that, for example, in 3-dimensional space, unit vectors are orthogonal to each other. For example, if you had a 3-dimensional coordinate system with unit vectors E x, E y and E z, they are all orthogonal to each other. That means that if I take the dot product of two vectors E x dot E y, I will get 0. If I take the dot product of the same vector with itself, Ex dot Ex, I will get 1. So, the inner product here which I have defined for you is analogous to the dot product of two vectors. Okay. So, therefore, the inner product is non-zero only if you take the inner product of one function with itself. If you take the inner product of one function with some other function, it turns out to be 0. Okay. So, in that sense, each of these functions is orthogonal to every other function. Okay. What are these functions? Okay. Within this domain, okay, I have z star in this direction. Okay. For n is equal to 0, okay, sin pi times z star, okay, it is equal to, so this is at z star is equal to 0 and z star is equal to 1. Sin pi z star is 0 both at z is equal to 0 as well as at 1, okay, it goes to 1 at a half. Okay. So, it has a behavior that goes something like this. Okay. Then I have sin 2 pi, okay, it shall go something like this, 3 pi, 4 pi, which will be a still higher harmonic, and so on. Okay. So, basically I have a series of functions, each of which is orthogonal to every other function within this domain. Okay. And this forms what is called a complete basis set of functions. Okay. So, any function in this domain, okay, for example, the functions that we had for the temperature profile, which would basically initially it was something like this, and then it decreased in time until it went to the final linear profile. Each of these functions at all intermediate times can be expressed as the sum of these basis functions multiplied by suitable constants. Okay. So, any function, just as in a 3-dimensional vector space, any vector can be expressed as the sum of the unit vectors times constants, the components times the unit vectors. So, one should think of these things as the unit vectors or the basis functions in this function space, and these as the components of that basis function. So, basically you are decomposing the temperature profile into a set of basis functions. We know that it is complete. Any function can be expressed as the sum of all of these functions. Okay. Each of these functions is orthogonal to every other function. Okay. And the only difference is that in vectors you have only 3 directions. In this case, there is an infinite set of basis functions. Okay. But as far as the analysis is concerned, that makes no difference. Okay. So, in my solution procedure, what I have done is to express T star of t as some summation of a n times S n times e power minus n pi the whole square times t star, okay, where S n is a function of z, it is equal to sine of n pi z. Okay. I know that at time t star is equal to 0, this capital T transient, okay, is equal to minus of 1 minus z star. Okay. Therefore, the summation a n S n, this exponential becomes 1 at t equal to 0. This has to be equal to minus of 1 minus z. The summation has to be equal to 1 minus z. Okay. Now, what I have done is I have taken the inner product of both sides with respect to S m. Okay. So, I have taken the inner product of summation n is equal to 0 to infinity of a n S n comma S n, where the inner product is defined as follows. The inner product is defined in this manner. Okay. So, I take the inner product of both the right and the left hand sides with respect to the basis functions. It's like saying if I have an equation which says that one vector is equal to another, I can take the inner product of both those sides with respect to the unit vectors. Okay. In a similar manner, I am taking the inner product of both of these sides with respect to the basis functions. Comma Sn. Okay. And since the An's are all constants, this is equivalent to writing summation n is equal to 0 to infinity of An times Sn comma Sm is equal to minus this inner product. Okay. And Sn and Sm are orthogonal to each other, and therefore, this is n is equal to 0 to infinity An delta Mn by 2. And delta Mn is non-zero only when n is equal to m. Okay. Therefore, this will give me Am by 2 minus and that was how I determined the constants, all of those infinite set of constants in the equation. Okay. So, this is analogous to just taking expanding out. Okay. So, this process of expanding out the system, the equation in terms of these basis functions here, I am expanding out the entire function or in the entire domain from 0 to 1 in terms of this basis function, equivalent to writing a vector in terms of the 3 basis vectors. Okay. In this particular case, you have an infinite set of basis functions, but any function can be expanded in that infinite set. Okay. The set is infinite, but there is no ambiguity in determining the components, and the reason is because these functions are all orthogonal to each other. If they were not orthogonal to each other, when I took this inner product, I would get a series of linear equations which involved all of these coefficients. However, since they are orthogonal to each other, these coefficients are non-zero only when n is equal to m, and therefore, without any ambiguity, I can determine what each of these functions is. Okay. These values, the values of beta n that I had is equal to n pi. These are called the eigen values of this problem. Okay. And this Sn, which was sin n pi z by L, okay, these are called the eigen vectors or the basis functions for this problem. And we have defined the inner product of this in such a way that these basis functions are all orthogonal to each other. Okay. And in that way, we have managed to determine the entire solution to the equation. Okay. Important points to note: at the beginning, I said that I require homogeneous boundary conditions in the z direction. Okay. The reason is because it is only with these homogeneous boundary conditions that I managed to get a discrete set of values of beta which satisfied this equation. Okay. It was only because I had homogeneous boundary conditions on both boundaries that beta was equal to n pi. Okay. So, it is important in all these cases to ensure that you have homogeneous boundary conditions in the spatial directions, in all directions except one. Okay. You have to reduce the problem to one where there is homogeneous boundary conditions in all directions except one, and that one direction, in this case the initial time t is equal to 0, that is where the forcing is taking place. Okay. And it is only if you have homogeneous boundary conditions that you will end up with a discrete set of eigen values, okay, and a discrete set of eigen functions. Okay. So, beta cannot take any value, it has to have a value of an integer times pi, and the eigen function has to be of this form. Okay. And for this particular equation, that eigen function with the orthogonality relation defined in this manner gives you an orthogonal basis set. Okay. And because the system is orthogonal, I can solve the equation using the orthogonality condition to find out each of these coefficients uniquely. Okay. And once I have each of these coefficients uniquely, then I know the entire solution. This solution is an infinite series. So, if you wanted to determine the solution exactly, you would have to determine an infinite number of terms. Okay. However, the higher order terms in this series decay as e power minus n square, okay, as n becomes large. Okay. So, for example, I could get a good numerical approximation to this equation by writing it T star transient is equal to summation from n is equal to 1, 3, etc., let us say up to p, some number p, p may be 50, 100 and so on, of 2 by n pi sine of n pi z star e power minus n square pi square t star. This is an approximate solution because I have cut it off at some particular value of n. I have neglected the higher order terms in this expansion in n. What is the error that I am likely to make because of this? The error will be equal to t star t minus the approximate solution that I have. So, this is going to be equal to the summation from p plus 1 to infinity of 2 by p pi sine is 2 by n pi sine of n pi z e power minus n square pi square t. Now, we do not know exactly what the sine function is, it is of course bounded, but we know that this has to be less than or equal to summation from p plus 1 to infinity of 2 by n pi times e power minus n square pi square t. That is because the sine function is bounded from above. The sine function can be at most 1. So, the error can be at most summation of 2 by n pi times e power minus n square pi square t. So, in the limit as n becomes large, I can actually approximate this as an integral dn into 2 by n pi e power minus n square pi square t. And if I define another variable, if I define n star is equal to n square pi square t to the half, which means that n is equal to n star by pi t star per half. Then this error has to be less than or equal to integral from p star plus 1 to infinity of dn star into 2 by n star by 2 by n star. E power minus n star square, where p star is equal to p plus 1 by pi t star per half. No, the other way. Where p star is equal to p pi t star per half. So, for a given time, I can always choose my p in such a way that the error becomes less than some specified value. So, as time progresses, the value of p that I choose will be smaller and smaller, because if this integral is fixed to a constant value, I can truncate my series at a smaller and smaller value of p and still get the error below a prescribed value. For example, if I wanted a 1% error maximum, I will have to choose my p depending upon the value of t in such a way that this integral is less than that. Okay. So, even though the series is infinite, I can use this to control the error in any expansion if I truncate it at some particular value in the series. Okay. So, we have theoretically got an infinite series, but in practice if t star is equal to 1, then this is a series which goes as 1 over n. Okay. But if t star is larger than 0, okay, if t star is equal to 0, then the exponential all become 1, but so long as t star is larger than 0, the higher order terms are going to decay exponentially as n increases, and therefore, I can truncate it at some point. The point that I truncate it goes to lower and lower values of n as time progresses. Okay. So, I can control my error in this manner and get a good numerical approximation for the separation of variables solution. Okay. So, we have looked in some detail at the separation of variables procedure. As I said, this is an important procedure, we will use it repeatedly later. I request you to go and revise this a little, okay, so that when it comes once again in later lectures, you will be familiar with this procedure and all the intricacies of this. I will briefly review this once again before we go on to another method of solving the conservation equations in the next class, and that is the method for oscillatory flows. If I had, for example, two plates and one was oscillated with some particular frequency, how do I find the velocity field within the entire domain? That we will continue in the next lecture after we briefly revise the separation of variables procedure that we conducted in this class. So, we will see you in the next lecture and we will continue unidirectional flows in the next lecture. Thank you.